So the next talk is on generating proof certificates for a language-agnostic deductive program verifier.
Xiaohong.
Yes, it's by Zhengyao,
Xiaohong
Chen,
yep.
who will be giving the talk.
Thank you.
Minh-Thai, Trinh, Wang, and Grigore, Roşu.
Yes, thank you.
So, looks like we're all set up.
Good. All right. Hello, everyone. Thank you for the introduction. So, and thank you for coming in on the last day of OOPSLA, in the afternoon. I'm Xiaohong from Verification. And the work I'm presenting today was actually finished when I was a PhD student at UIUC with my UFI colleagues, Zhengyao, Minh-Thai, John, and Grigore. And since then, Zhengyao, me, and John have all graduated. So this is why we have some sort of like diversity there in the affiliation. All right. So our research work is about making formal verification results more trustworthy for all programming languages using proof certificates. And this research is important because we have issues of having large trust base in formal verifiers. And this is because program verifiers are very complex programs themselves, so it is very difficult to prove them correct. And usually they are not based on a form of semantics. So even if we want to prove them correct, we don't know what correctness means here. They are correct with respect to what? Now, what we know is that sound and complete formal verification for all programming languages is possible. And it has been implemented in the K framework, which I'll talk about later. And we also know that K has a very small logical foundation called matching logic. However, actual reduction from K's formal verification algorithm to matching logic proofs has not been studied. And this is what our work is about, right? So we formalize formal verification results using matching logic formulas. So they are the claims we want to prove. And we translate executions of the formal verification algorithm into matching logic proof certificates. And these certificates can be checked by a very simple program called a proof checker, which has only 200 lines of code. And by doing that, we bring more trustworthy formal verification to K, and we reduce trust base from the previous 120K lines of code to this 200-line proof checker. And we tested our methods on various programming language paradigms, including imperative, functional, and assembly languages. And the conclusion is that we can give efficient proof checking for formal verification. Now, in the rest of my talk, I'll spend more time in describing the background, the context of work, and then I'll show you some technical details. So the first thing I want to say is about K. So formal verification is done in a language-agnostic way in K, just like everything else. So as you can see on the right, so this is the K framework. It's a collection of these language tools. We have interpreter, compiler, model checker, symbol executor, and of course, a program verifier. Now, what's interesting is that these tools are all parametric in a formal definition of a language. So you can define your programming languages as a formal semantics, and you can pass them as input to the framework. And the framework instantiates these tools based on the language you give it to them. So this is why we have, so this is what we call the K framework. It's a language framework. You can define the semantics of language in it. You can generate tools from it. And here's an example K semantics of a very simple imperative language called imp. So this is like the hello world example in PL. And it has two modules. It has a syntax module, a semantic module. In the syntax module, we define a concrete syntax of this language using BNF grammar. So for example, here's the BNF grammar for expressions and for statements. So you can see that we have, for example, assignments, if and else, while loops, and so on. In the semantic module, we define configurations. So this is like the state of the program run in this language. And for imp, the configuration is very simple. It's just a pair of the program, the code to be executed, and a map from program IDs to their values. And then we have all these rules. They're called semantic rules. And they define the operational semantics of a language. For example, the first rule says it's a lookup rule, right? So it says if I see a program ID X in some evaluation context, and the program state is map M, then I'll rewrite X into M of X. I'll look up its value in the map. So this tells how to look up a program variable in the program map. And we have all these rules. They are written in this like a small step semantic style. So it's very, clear to see how we can use this semantics to execute programs. Now you may ask, okay, this looks great. This semantics executable. How does it relate to formal verification? Well, it turns out that you can use exactly the same operational semantics to do formal verification. So actually, K's formal verification algorithm is entirely based on such operational semantics. So somehow there is this myth in formal methods that operational semantics are only good for execution. If you want to do formal verification, you need another semantics, like denotational semantics or whole logic or axiomatic semantics. Well, that's not true, right? So operational semantics is all you need to do sound and complete formal verification. And let me show you how we can do that. So suppose we have this simple program. It's a sum program. It has a while loop. All it does is to calculate the total from 1 to n, where n is this symbolic input. And we can write the spec of this program as what we call a reachability claim. So let's say that for any value n, if I start with a sum program and empty map, then eventually I will reach this final configuration where I have no computation left. So .k means nothing, right? So there is all the computation, all the code has been executed, and the map looks something like this, where S maps to the total sum from 1 to n. Now, in order to prove this spec, of course, I need to write down the invariant for the while loop, and this looks like something like this for any S and n. If I have the loop and I have any map, then eventually I will consume all the code, and maps is updated like this. Now let me show you how I can prove this invariant using nothing but just the operational semantics of your language. Okay? Of course, the first thing is I have a loop. So I have two branches, whether I get into the loop or not. So let's say we get into the loop. And that's here. So we have a side condition, n is greater than 0, and then we have the body of the loop itself, and the same thing. Okay? And now we can use symbolic execution to consume these assignments. And we see the loop again, but the values of S and N are updated. Now here's the interesting thing. So let's compare this with our invariant. Well, you will see that, okay, the invariant tells me that this holds for any S and N. And what happens here, I have a different value of S and N, so I can instantiate the invariant to prove the subgoal. And this step is called co-induction. So because you're using the invariant to prove one of its subgoal. And this is sound because we are making some step, right? So we're making a progress, so that's guaranteed soundness. And by doing that, we have something like this. This is the right-hand side of the invariant instantiated, and this is the original right-hand side. And we see that, okay, everything else is the same, so I just need to prove this equality about integers. I can do that using SMT solvers or some domain reasoning tools. So what I'm showing here is that I can use operational semantics with symbolic execution, with co-induction. So this is the step where I prove a subgoal using the claim I'm proving. And this gives us full formal verification for all programming languages because it's based on the formal semantics of a language. Now you may say, well, this looks great. You have a program verifier for all languages, and because it's based on semantics, so it is sort of like correct by construction. So what else? Well, the issue is that K has a very large code base, right? It's over 550K lines of code. And at least 120K lines of them are directly related to symbolic execution and formal verification. Of course, there are more things about non-symbolic execution and front-end and others. So the motivation here is, can we at least do something to this large trust base, right? It's just too big to be in our trusted code base. Can we do something there? Our solution is to reduce K to something simple, a logic. And in particular, we use matching logic. So matching logic is this variant of first logic extended with fixed point and second order variables. It's very, very expressive. So you can express all these existing logics, calculate type systems, including K. All of them are definable as theories in matching logic. And what matters to this work is that matching logic has a very simple proof system. So here's the matching logic proof system. If you are not familiar with logic, don't worry, we'll not get into it. So what you see here are what we call the proof rules. And matching logic has only 15 this kind of proof rules. And what they do is they define this provability relation between axioms and the claim. So think of these axioms to be the programming language semantics you have. And the claim would be this the spec of a program or this invariant property you want to prove. And And this proof system is what we call a Hilbert-style proof system. And that means the proof has a very simple linear structure. It's just a list of formulas, one by one. And every formula is either an axiom, or it is the result of applying some of the rules to the previous things. So the conclusion of that is it is extremely easy and simple to check the correctness of such a proof. And the program that checks the proof is called a proof checker. And we implement the proof checker for matching logic in only 200 lines of code using this language called MetaMath. So the conclusion is matching logic is a very small, simple logic. It has a very simple proof system. So it has a very small trust base when it comes to proof checking. Okay? Now, how does it relate to K? Well, we can really think of K's deductive verifier as a matching logic proof searcher. So imagine this is the set of all matching logic formulas. Some formulas are programming language semantics, so they are axioms, they are assumed. And the claim I want to prove about my program is out there. So the question is there a proof using the proof system? So I'm trying to find such a proof. If I find it, this red line is going to be this proof certificate, and I can pass it to the checker. The checker will check the correctness of it. And how do I get to this red line? Well, I have the verifier. And the program verifier is kind of taking the bigger steps. Why? Because the verifier operates at a more higher level, more abstract level. So it takes these execution steps, but it can be regarded as a hint, a guidance. It is a proof searcher. It's the best effort heuristics to find such a proof. So I can really reproduce from the blue trace the red trace. And this part is called proof generation. We generate proof certificates to kind of fill in the gap between the execution steps of a verifier and the actual mathematical, logical proofs. So our main contribution is a set of proof generation procedures. So the first one is about symbol execution, and actually it all boils down to proving the correctness of one-step execution. So basically, if I have a semantic rule, left-hand side versus right-hand side, from that I can prove this claim where I instantiate it with some substitution theta. And besides that, I also need to prove transitivity, branching, case analysis, all these useful lemmas. The second one is what we call the pattern subsumption. So it's essentially implication between two formulas. So we've seen this example before. I end up with something like this after co-induction, and this is my original goal. So I need to do some sort of pattern matching, and to realize that, I just need to prove that these two expressions are the same. And finally, we need to do co-induction. So this is sort of the essence of formalification. And for that, please read our paper for more details. Okay. All right, so let me show you the workflow. Okay, so the workflow is we start from the definition of a language, say imp. And we start from the environment or the spec of a program we want to prove. And we run these proof generation procedures on top of it. Right? And the output is going to be this matching logic proof certificate, which includes all the detailed mathematical proof steps. And then we can pass it to the 200-line proof checker. And if a checker says yes, then we know that the claim is actually correct. And notice what's happening after we do this. So firstly, we remove the K verifier from the trust base. You no longer need to trust K anymore. And secondly, you don't need to trust these proof generation, you don't need to trust the proof generation procedures either. Why? Because all of them are just part of the proof search process, right? They're heuristics to find such a proof. What's important is I somehow get the proof certificate of my claim, and this certificate is correct. It's automatically checked by the checker. So that's all I need. My trust base is the checker. K and proof generation, they're just part of the heuristics. Okay, so I'd like to wrap up with some evaluation. So we did we had implementation, and we did some preliminary experiments on it. So the main takeaways are, one, our methods is language agnostic. So we tested on imperative functional assembly programming languages. So this is why, for each program, there are kind of like 3 versions of the same program there. And we achieve efficient proof checking for formalification. So if you look at the last column, so this is the time in seconds that we need to check, the proof certificates for formalification. You can see that's mostly done in a few seconds. And what's interesting is that if we compare the time with the time that K uses to verify the program, you can see that sometimes it's actually faster. So it's actually more motivated to generate the proof certificate and to check it using the checker rather than run the verification algorithm again. Because one, it's faster. Two, it's actually, it has a smaller trust base. And three, it's easier to do so because you don't need to set up the entire K pipeline to do that. You just need to set up this 200-line checker. Okay. So to conclude, our work brings more trustworthy form of verification in K. So in this sort of like a translation validation style. And what's interesting is that our work is language agnostic. So we are not specific to a particular programming language, but instead we are based on an open semantics of the language. So it works for all programming languages. And by doing that, we reduce the trust base of form of verification in K from 120K lines to this 200-line checker. And by doing that, we also found bugs in the K framework, like missing axiom, etc. So overall, we make K more trustworthy. So that'll be the end of my talk, and I'm happy to take any questions from you. Thank you. Yes.
Hello, thanks for your very nice talk. Your slide, you do not show the size of the code because I see the specification. So I see the size of the proof.
Yes. So
but the code that you check. So where is the size of, for example, in number of lines? To have an idea.
You mean the size of the program?
Yeah, the size.
Oh, it's mostly here. So they're very, very simple programs, right? So
okay, because this is written spec, so it was not clear for me what
the
means
spec. Yeah, so the spec includes the program and also the property, right? So the program plus the property you are proving.
And are you not worried of the difference between the size of the initial program and the size of the proof?
The size
because these are megabytes, or?
Do you mean there are two numbers here?
So what are the size of the proof here?
Oh, it is the size of the output, the proof certificate that we are generated. So the first one is the one before proof compression, and the second one is after proof compression. I didn't talk about proof compression, but because proofs are encoded in this text-based format, so if you run just some compression algorithm on it, you can get very, very good improvement on that. But essentially, you can think of the size as this is the size of a proof, the mathematical proof, right?
Okay.
So yeah, so if you write down mathematical proof one by one, so it's
so these are in megabytes.
Yes.
Yeah.
Yes. So and this is encoded in this language called Mellon. So it's a formal language that allows you to write abstract mathematics and proofs.
Okay.
Yeah.
And so what do you think of the size of the proof with respect to the size of the input program?
Yeah, the proof is huge, and the reason for that is the logic, right? The proof system is at a very low level, so we really reduce the execution of programs down to the basic level of logics, right? Okay. So somehow there is a balance between how if you have a very advanced proof system with many fancy features, of course you have shorter proofs, but the proof checker will be more complicated. So what we want is, can we make the checker to be as small as possible, right? And for that, the cost of that is the proofs are going to be slightly bigger.
Thanks.
Yeah. Thank you for the question.
Let's maybe you can take your computer and we get the next speaker up, and then we can answer the next question. You want to ask the next question while we're setting up?
Thank you. You were speaking about the co-inductive step. Is that part of the case system, or that you need a co-inductive step, or is it in particular for this approach where you have got the proof certificates and you check the certificates?
So we need co-induction to do formal verification in general. What's interesting in our case is we have only one rule for co-induction. So it's a co-induction for all programming languages. So if you see classic approaches like whole logic, if you have a while loop or if you have like a recursive function calls, the corresponding whole proof rule is actually doing co-induction, but for that particular language construct. So what we have here is a very general rule called co-induction that can give you, complete formal verification for all languages. Yeah. But it's part of our framework, right? So the framework has this co-induction ability. All right. Thank you.
All right. Thank you.